All right, good afternoon, everyone. Welcome to another lecture. So today we have quite a different problem to address, but before we jump right into it, as always, let's briefly recall what we've done the last time. So last week we started looking at the radiation problem. We derived the free space Green's tensor of the Helmholtz equation, and applying this Green's tensor to a point dipole, we characterized electric and magnetic fields radiated by point dipole, point electric dipole in free space. We studied in details its spatial fields that this dipole creates. Using this Green's tensor, we calculated total emission intensity of a point dipole, and then using the expansion of these fields into a set of vector spherical harmonics, we developed a tool called multiple expansion, which allows us to quantify the angular distribution of electromagnetic field created in free space by an arbitrary set of electric currents and charges. And then using this multiple expansion, we described an intriguing phenomena called non-radiating sources, where a certain non-trivial configuration of electric charges and currents does not produce any fields in the environment because of the destructive interference. So all of that I just described and that we talked to you about the last week was done basically in free space or in any kind of homogeneous medium. For example, we could easily write the Green tensor for a homogeneous dielectric and obtain pretty much the same result. But sometimes we have an emitting system, for example, a point dipole, not in a homogeneous medium. For example, we can have a dipole over a substrate, over a 2D material. We can have a dipole close to nanostructure, and we would like to have a tool that will give us a solution to the corresponding radiation problem. And today we're going to start addressing such radiation problems in more complicated scenarios. And we could ask, what is the simplest problem? What is the simplest non-trivial radiation problem, non-trivial geometry in which we could address or try solving the radiation problem? And the simplest geometry is, perhaps the simplest geometry is a point source placed above an isotropic substrate. So we have two half spaces, the upper half space and the lower half space. The upper half space is vacuum, air, and the lower half space is filled with some homogeneous and isotropic medium, which can be a dielectric, a metal, magnetic, anything that is characterized by certain permittivity and permeability. We're going to be assuming that this is a non-magnetic material, and the dipole is located a certain distance L above this substrate. The dipole can have arbitrary linear, circular, elliptical polarization. The question is, what should we do in order to find the electromagnetic field produced by this source, by this point source of electromagnetic field in this environment? And this, in a way, looks like what we have addressed already a few lectures back when we were looking at refraction and reflection of a plane wave incidence on an interface, at an interface between two semi-infinite media. And here we have essentially the same geometry, just instead of a plane wave, we have a point dipole. And, well, naively, one could think that this point dipole produces some kind of plane waves. These plane waves are getting reflected, transmitted by the interface, and we could deal with this problem in a similar way. But the reality is this problem is much more complicated. The reason for why this problem is much more complicated, technically, mathematically, is because a point dipole, unlike the problem that we've addressed previously, does not produce a single plane wave. It produces a divergent spherical harmonic. It produces an outgoing spherical wave. An outgoing or convergent spherical wave does not have a certain wave number k. And what allowed us to solve the reflection and refraction problem with the plane wave in such an easy way is that plane wave is characterized by a single wave vector. And wave vector is the in-plane component of the wave vector is preserved in the case of a translationally invariant substrate. And this allows us to construct the scattering solution very easily. But this is not the case with the point dipole, because now we don't have any k at all. We have a divergent spherical wave. So what are we going to do? Well, luckily, there's a tool that allows us to go from a spherical wave to plane wave representation. And this is what we're going to learn first before we handle this problem. So how do we go from an outgoing spherical wave to the plane wave representation? The tool, the identity called Weyl identity, comes to rescue. So this is Weyl identity, which expresses an outgoing spherical wave. Remember, this is the same as the scalar Green's function. All right. So this identity expresses this G0 as a double integral over plane waves with different kx, ky, and kz. And this is double integral which runs over kx and ky. And for every pair of kx and ky we substitute, we plug into this integration, kz is determined from here, okay? And notice that we have a square root here, and as you know, the square root has a branching point when the argument of the square root equals 0. And that determines two possible Riemann sheets of the square root function. And I think, as you know from previous lectures, these branching points and the choice of Riemann sheets of the square root needs to be dealt with very accurately. We're going to have to choose only one. And on the next slide, I'm going to show you which of these two sheets we need to choose in order to obtain a physically correct expansion of the outgoing spherical wave. So notice another interesting thing is the presence of this factor in the integral representation of the spherical wave. This is so-called two-sided wave. You see, it's not just e to the power I kz z. It's the absolute value of z, which means that if we have the z equals 0 plane here, and we have our source here in the origin, then we have this half space where z is positive and the lower half space where z is negative. And we're going to obtain kz in the same unique way for both half spaces, but here we're going to plug this absolute value, which is the same as z, and here we're going to plug absolute value of z, which is minus z. So essentially, we obtain two different expansions in this semi-space and in this semi-space. Again, this is due to this unique two-sided wave which appears in this in Weyl identity. Okay, so let's write Weyl identity one more time. And here is the rule that determines which Riemann sheets of the square root function we need to choose. So when k squared exceeds kx squared plus ky squared, we're gonna take the square root with a plus sign, the usual definition of the square root. And this region, when k squared exceeds kx squared plus ky squared, is called the Ewald sphere. We are inside the Ewald sphere. So this is the propagating region where kz is real valued, and that corresponds to waves, homogeneous waves traveling in different directions away from the source. But outside the Ewald sphere, where k squared is smaller than the sum of kx and ky, this is called the outside the Ewald sphere, and kz is calculated according to this, which gives us an attenuating evanescent wave, attenuating in both the negative and the positive direction of z. So when you plug these two rules for the kz into here, you're going to see that what this expression produces is a sum of different propagating and evanescent waves that decay in both directions of the z-axis. Why the z-axis? Well, because that was our deliberate choice. we chose to expand this spherical harmonic over kx and ky, and this makes the z-axis special. That is why the waves that enter this expansion, they decay in the z-axis. So essentially, what we obtained by this expansion is the composition of a single spherical wave, outgoing spherical wave, into a continuum of different plane waves with all possible kx, ky, and for every kx, ky, you calculate the corresponding kz, integrate all these contributions with the corresponding weight. You see this 1 over kz, this is the weight of every plane wave with which it enters the entire expansion. And that, in the end, when you perform the double integration, gives you the spherical wave. And this is the graphical representation of the expansion that we just performed. Again, we have a source. It creates an outgoing spherical wave. We choose the z-axis that determines a certain z equals 0 plane. And then the Weyl expansion, the Weyl identity tells us that the spherical wave that this thing creates can be expanded into a set of propagating waves with different wave numbers and set of evanescent waves that decay in both directions along the z-axis. And the integration of this result restores the original spherical wave. Okay, that was the scalar Green's function, G0, or the scalar expansion of the scalar spherical wave. But a dipole produces not a spherical wave, it produces a vectorial spherical harmonic, it produces vectorial electromagnetic fields. So how do we expand our vectorial fields? Well, let's now place a linearly polarized dipole with arbitrary polarization in the origin, and we can calculate the vector potential that this dipole produces according to this. So this is just some fixed vector. This is our spherical wave that we just expanded using Weyl identity, okay? Now let's calculate the electric field that this dipole produces. Well, once we know the A, we can act on A with this operator, which is 1 plus gradient of divergence. This gives us the electric field. So what we need to do is that we need to expand this to represent this using Weyl identity and act with the differential operator on this thing. And that will give us plane wave representation of the electric field, of the vectorial electric field. Let's do this. So we're gonna write the plane wave representation of the Green's tensor in this way, where this is the same factor that we already dealt with. I explained to you that this is a bunch of plane waves propagating in different directions, where the absolute value describes the two-sided plane wave, and kz is determined according to certain rule. So, and using this definition for the electric field, we obtain the following form for this M dyad in the K space. So this, in principle, is the answer to the problem. This gives us the expansion of the Green's tensor of a point dipole in free space as an integral representation of different plane waves propagating with different wave number in different wave vectors in different directions with different weights. And M, along with this factor, determines the weight with which every component is. It determines the weight and the polarization of every plane wave component. So notice that I have two signs for this dyad M here, plus and minus. This is because this expansion, like I said, is basically two separate expansions in this semi-space and in this semi-space. The expansions are different. And because the electric field contains the null operator, the divergence and the gradient, it's going to act differently on A. To be precise, it's going to act differently on this little guy, AZ. Because this involves differentiating over Z in particular, and because we have the absolute value of Z, we can obtain two different signs in two different half spaces. This is why we have plus and minus sign here, and the plus and minus sign enters the definition of K plus minus. See, we have K plus K minus, and K plus K minus are determined according to this. The reason why plus and minus appear is because the nabla, the divergence, acts on the two-sided plane wave, which results in two different signs. So the upper sign in this expansion and in the following expansions applies to the upper region, and the lower sign applies to the lower region. That's simple. Okay, so this in principle answers the question of expansion of the Green's tensor into plane waves. So what we have is, this is the representation of the same diode, M plus minus, in a Cartesian system. If we were to represent it in a basis of, in a Euclidean system, we would obtain this. And this expansion is known in electromagnetism as the angular spectrum, the compositional angular spectrum representation. And at this point, I want to emphasize that what we have obtained is different from the Fourier representation of the same Green's tensor. We obtained the Fourier representation the last time, 1 week ago, and it looks like this in free space. This is the true Fourier image of the original free space Green's tensor expressed for every frequency expressed in the K space. And this is the angular spectrum representation. So probably you can see the difference. This, to get this, we freeze time, we choose a certain frequency, and we obtain certain spatial picture. And then what we do in order to obtain a Fourier representation of any picture, we do Fourier transform. And in this case, we have three spatial coordinates, x, y, z. And what we obtain in the end is a function of kx, ky, and kz, where these three numbers, these three quantities, run over the entire range of values in three-dimensional space. So we can have a very small case, a very large case, and so on and so forth. There are all possible cases. So at this point, we don't care about frequency. What we have is certain spatial picture, and we perform a Fourier transform of that picture in real space. And of course, we obtain all spatial frequencies in the end. This is the trivial Fourier transform. But this is different. What we done here is only a double integral. So we have all possible kx and ky, but we don't have all possible kz, because for every kx and ky, kz is determined automatically according to the rules that we formulated ago that shows a corresponding and appropriate Riemann sheet of the square root. So that's not a Fourier transform. That's just some representation of the same function over all possible kx, ky. And furthermore, it's also different in the upper semispace and in the lower semispace because of this, right? If we had a true Fourier representation in its true sense, we couldn't have the absolute value of z here. We should have had this kxx plus kyy plus kzz, but you have the absolute value, because that's essentially two different representations, above the interface and below the interface. So this is not a Fourier. This is just some very handy way to represent our field, to represent the Green's tensor as a sum of different plane waves And all plane waves entering this expansion, they satisfy k dot k equals omega c squared. Propagating, evanescent, no matter what, all of these waves satisfy the dispersion relation. And remember that for evanescent waves, the k dot k and absolute value of k, they are, of course, different for evanescent waves. But this, we have all possible values of k dot k, all possible values, very small ones, very big ones, the entire range. All right? So I just wanted to emphasize that these are two different things and you shouldn't confuse the two. One of them is the true Fourier transform, and this is not Fourier transform, this is something else. This is called angular spectrum decomposition. All right, now let's talk about polarization properties of this expansion. We have expanded the fields into two contributions. Not into two, we expanded into a continuum of different plane waves. And like I said, each contribution to this representation has a certain spectral weight and also polarization. So let's talk about polarizations of these contributions. And for the following, it will be very convenient to split this expansion into two parts, into S-polarized and P-polarized, because plane waves, when they are incidents on an interface, they naturally split into two polarizations, TE and TM. And for the problem that we're going to deal in the following, it will be necessary to split the fields into S and P polarized parts. So how are we going to do this? Well, we need to project our field. So we need to project basically this into S and P polarized parts. But to begin with, we need to define what S and P polarizations are in this problem. And in free space, when there is no interface, you cannot define S and P polarization because all polarization vectors, they are absolutely equal. To define S and P polarization, you need a certain plane. You need either an interface, or you need certain axis, or you need the incidence plane. And we do have such a plane because we do have the z-axis and we have the z equals 0 plane. So we can easily introduce two orthogonal polarizations, and they will be distinguished by the presence of the z-axis in our problem. So these are the formulas that introduce two polarizations. S polarization is perpendicular to the z-axis and to the wave vector. So if you have a wave incident on a flat interface like this, then S polarization is parallel to the interface and it is perpendicular to the z-axis and perpendicular to the wave vector. So this is how we determine ES. The vector product, the cross product of z and wave vector, and we normalize it by this magnitude, and we obtain the following expression, Cartesian representation of the unit vector describing as polarization, where k parallel equals kx squared plus ky squared. And this is the graphical representation of S polarization for a certain wave vector. This is the z-axis, this is the wave vector. And similarly, P polarization should be perpendicular to both the wave vector and S polarization. So we take the cross products of these two and obtain the following. Okay? So these expressions are valid in both the propagating region inside the Evelt sphere and outside the Evelt sphere, that is in the evanescent or the near field region where k parallel exceeds k. So moving on, another interesting property is that these expressions, they describe an orthonormal set of polarization vectors, that is ES dot ES, and the same for P polarization, they equal 1, whereas as.ep equals 0, which expresses the fact that they are perpendicular to each other in the generalized sense of the dot product, because not always these vectors will be real valued. Sometimes they will be complex valued, because kz that enter this expression, they may be complex valued in the evanescent region, or it can be imaginary. So these vectors may also have imaginary as well as complex components, and so they will be perpendicular or orthogonal to each other in the sense of the unconjugated dot product. So let us look at the resulting polarization of these vectors. If we plot these vectors ES and EP that are introduced previously in the kx-ky plane, we can obtain two qualitatively different pictures. Let's go one by one. So we'll start with S polarization. As you remember, S polarization needs to be perpendicular to the y vector and to the z-axis. And so this is our z-axis. The y vector lies in the xy plane, and you can see that obviously for every point inside the Evolt sphere and outside the Evolt sphere, the polarization vector of the S component is clearly perpendicular to both, and this is satisfied. And another interesting property is that no matter where you look, this polarization, this vector describes linearly polarized light, both inside and outside the Evolt sphere. So the picture is different for P polarization, strikingly different. So inside the Evolt sphere, we still have a set of linear polarizations, but it drastically changes as we go outside the Evolt sphere to the evanescent region. So this is where light becomes evanescent, and the z components of the wave vector in the angular spectral decomposition is now imaginary, and this gives elliptical, generally elliptical polarization to our P polarized component only outside the Evolt sphere, which remains linear inside. And first of all, it gives a certain longitudinal component to every vector, which lines in the plane, okay, and parallel to the wave vector. And these ellipses, as you go far away into the near field region, they approach ideal circular polarization in the deep near fields when K parallel approaches infinity. So P polarized component becomes almost circularly polarized in the limit of large in-plane wave vectors. Okay, so now finally what we can do is that we can write the angular spectrum decomposition of the free space Green tensor in the following way, where we explicitly split the fields into S and P polarized parts, and expressions for MS and MP are presented in earlier slides. And yeah, this is the full answer, the final answer to the problem. We don't have any substrate yet. Remember, we are still dealing with the problem of free space. We don't have the substrate. This is just the expansion, angular expansion of the fields in free space, where we clearly, explicitly separated S and P polarized parts and managed to write the total vectorial fields as integral representation of certain diodes acting on our arbitrarily polarized dipole located at the origin. Yeah, and then we need to yeah, I think we haven't obtained these expressions, right? Yeah, I forgot, we haven't obtained these expressions. We still need to obtain them. And in order to obtain them, we need to project electric fields into S and P polarized parts, multiply again, and then this we can write as direct product as always. And this thing and this thing will give us the explicit expressions for this, okay? And this is easily done because we have expressions for ES and DP, and the result takes the form. So this is the angular spectrum representation where we separate S and P polarized parts. And these diodes, they have the following very cumbersome form. You don't have to remember it. I don't remember it myself. These expressions here are just for the reference to complete solution of the problem. So like I said, this finalizes our problem that I posed in the beginning. We wanted to know how to expand a certain a field of a point dipole in free space, how to expand it into a set of propagating and evanescent plane waves, and how to distinguish their polarization. And this set of expressions answer that question. And now we can go back to the Sommerfeld problem with the emission above an interface. So what we're going to do now is that we're going to consider our dipole located at the origin, and we're going to add the interface characterized by certain isotropic permittivity, and we're going to try to solve this problem. The problem has a very curious history, and I think I mentioned that already a few lectures ago when we were discussing the problem of surface waves. The problem was originally addressed by Sommerfeld in 1909 in relation to radio wave propagation in the atmosphere and the question of how radio waves can propagate along the surface of curved Earth over the horizon. And it was hypothesized that surface waves carry part of the energy, and to rigorously address the problem, one had to solve exactly this radiation problem with a dipole, which modeled a radio antenna placed above the Earth, which was modeled as a flat substrate. And there was a lot of controversy in that year related to that problem, and then it was revealed that the original paper by Sommerfeld contained a sign error, which was revealed only some 10 or even more years ago. So it was quite a messy problem with very long and interesting history. But anyway, a few decades after that, after the original work, the problem was finally solved without any mistakes. And now we can utilize this solution, and in the following I'll try to present only part of the solution, because the problem, like I said, is quite sophisticated, and I'm going to try to outline only the general recipe of solving this radiation problem. Okay? So this is the scheme how we're going to solve the problem. We're going to solve it by using the scattering superposition method. So if you, for a second, forget about the substrate, we have our dipole, which creates the so-called primary field. The primary field is the fields of the dipole alone without the presence of any substrate. And these fields can be expanded using the angular spectrum decomposition into a set of plane waves propagating in the upwards and downward directions, a set of both propagating and evanescent waves. And as long as we don't have any substrate, this is the answer. But now we do place a substrate, and what happens is that the primary field radiated by the dipole starts interacting with the substrate. And the way it interacts with the substrate, because the primary field is a set of different plane waves by nature. You just saw that in our previous slide, in one of the previous slides. And so what happens, these plane waves, they start to reflect, they start to be getting reflected and transmitted into the substrate. And what we need to do is to accurately describe reflection and transmission of every plane wave entering this expansion. And there are continuously many plane waves, and we need to accurately describe reflection and refraction of every plane wave, whether it's a propagating homogeneous wave or whether it's an evanescent wave. We need to accurately do both for two polarizations, for S and P polarization, to bring all that back together into a single piece integrate over all in plane wave vectors a parallel, and that would be the answer. So probably you can start understanding how technically tedious and meticulous this problem is, but that is because the problem combines in a way two incompatible geometries, because it combines something that is translationally invariant, the substrate, the interface, and something that has a spherical symmetry, the field of the dipole, which is described by the spherical harmonic. And when we bring these two geometrically different things together, such nasty things usually tend to happen when we try to solve them. Okay, anyway, let's try to address this problem. So we separate the region into two, the entire region into two domains, into what's above the interface and into what's below the interface. And this we're going to be denoting with the sign greater. For example, we're going to write E greater, and this is E lesser. All right? And we're going to write now the Green's tensors that describe the fields into both domains, into upper and lower domain. So this describes the total fields in the upper domain where Z exceeds minus L. And the field in this domain is given by the sum of the primary fields, which is not affected by the substrate in any way. This we already know. This is the simple angular decomposition of the fields without any reflection and transmission. And the reflected field. So the primary field is described simply by this, by the M dyad, M plus or minus, depending on where we calculate the field. So let's actually let's try to copy this sketch onto this blackboard, because we're going to be referring to it a lot during as we solve the problem. Okay, so we have the Z, we have Z equals 0, we have the interface at Z equals minus L. We have the dipole P, which produces this, it produces this, and I'm going to skip evanescent. So this is E greater, this is E less. I'm writing the electric fields here. In the lectures, in the slides, I have Green's tensor, and the electric field, of course, can be obtained straightforwardly by acting with the Green's tensor on the dipole. So my aim here is to obtain the dressed Green's tensor, which accounts for everything, for all reflections, refractions, so that by acting with G greater on the dipole, I'm obtaining the full electric field, the total electric field in every region. So here, M primary is the ordinary M dyad, which we obtained previously, which consists of, which is a sum of two polarizations, S and P polarization, and we use M plus or N minus, depending on whether we calculate the field here. In this region, we need to use M plus because Z is positive, and in this region, we need to use M minus. That's it. Then this guy, M reflected, is another unknown dyad, which yet needs to be determined in the following, and it describes the reflected field in this domain of the problem. And here, instead of the two-sided wave, we have an ordinary wave factor, because reflected field propagates only in the upward direction. It doesn't propagate downward. So we don't need to use the two-sided wave. Instead, we can use only the ordinary one-sided wave, if you will, because the field propagates strictly in one direction, because it is a reflected field, no matter if we are looking at the reflected field here or here. And this guy is the phase delay that reflected field acquires as it propagates here, gets reflected, and then propagates here. So this is delta, which is, so 1 delta is KZL. This is simply the phase accumulation that light accumulates before it gets back to Z equals 0 plane. Okay, this is as simple as that. Similarly, in the substrate, we're going to describe the fields by the G lesser Green's tensor, which can be described in a similar way using the product of a certain unknown dyad and transmitted, which will describe the polarization properties of the field here. Then only single phase accumulation factor, because before the field reaches this interface, it needs to travel only once. It doesn't need to travel back. So we have only e to the power I delta without the 2. Okay? Then we have the ordinary. The parallel wave factor. And then we have also this. This is interesting because the z components of the wave vector in the medium, in the substrate, will be different. This substrate is characterized by certain permittivity epsilon. And so we need to establish a different rule for calculation of z components of the wave vector in the substrate. And these are the rules, and they are chosen in this way in order to satisfy the radiation condition. In other words, that these waves, they carry radiation into the substrate and they decay exponentially into the substrate. Otherwise, we would obtain an unphysical solution. And so this is how we choose Kz in the substrate. We plug this Kz here, and in this wave, we have not simply absolute value of z, but z plus L, because the wave starts to propagate in the substrate only after it reaches this plane. So if we plug z minus equals minus L, then this will be equivalent to e to the power I delta times e to the power I a parallel x plus az z plus L. But because at the substrate z equals minus L, this is 0. And this is the correct result. So the only phase accumulation that this portion of the field has is due to this trip from the source down to the substrate. And then it starts to accumulate the phase in the substrate, which is described by this factor. Quite messy, I know there's a lot of different contributions, but stick with me. So now we are in a position to actually determine these unknown dyads for the reflected fields and for the transmitted field. So let's do this. The reflected fields, the dyad for the reflected field simply can be obtained by acting with reflection coefficients on the incident fields. So we have a plane wave incident at a certain angle in the substrate, and it is getting reflected. It is reflected with certain coefficient that is determined by the problem that we already solved a few lectures ago. This is the Fresnel coefficient. And for S polarization, Rs relates the electric field amplitude. And because we are dealing with electric Green's tensor, for S polarization, this is simple. We multiply this part of the radiation, m plus s, we multiply it by the Fresnel reflection coefficient, and this gives us the spectral weight of reflected fields for S polarization. But for P, you can see that I deliberately wrote a certain dyad, a certain tensor. Why is that? Why couldn't I simply write Fresnel's P times this P dyad? Well, that's because for P polarization, Fresnel's coefficients relate magnetic fields. But the Green's tensor, we're dealing with the electric Green tensor. So we can't use RP, that would be wrong. we need to do something else. And in order to do that, we need to derive certain operator that relates the Cartesian components of the electric fields of a p-polarized wave. This is quite tricky. Follow me once again. So we have a p-polarized wave incident on an interface. This is P, and a reflected field looks like this. So obviously, it's going to have different Cartesian components, and we need a tensor, a diagonal tensor, that will relate this vector to this vector. But what we only know is the scalar that relates the magnetic field. A magnetic field is very simple. So we're going to derive this tensor from the knowledge of the Fresnel's scalar RPs. And this is how we do this. So RPs relate magnetic fields. Reflected equals RP times H incident for p-polarization. This is textbook problem. And we derived RPs on one of our previous lectures. Now what we need to do is we need to relate the electric fields to the magnetic fields for the reflected and for incident waves. And after we do this, we combine this with this, and that allows us, after we do all the math, that gives us the following tensor that actually does relate the electric fields of the reflected p-polarized wave to the electric fields of the incident p-polarized wave. This is something quite unusual, which isn't often done, but because we are dealing with such a complicated problem, we have to do this exercise and learn how to relate electric fields of p-polarized waves. And this is in this geometry, in this isotropic geometry, this is described by the following tensor, where minus signs, this and this minus signs, which describe relation between x and y components, they can be understood very easily because, just like I tried to illustrate it on the previous slide, if we have a p-polarized wave, a reflected wave, as you can see, the z components of the electric field, this is electric field, this is electric field, this is k, this is k. It sort of remains the same, but the x component flips, because here the x component is directed this way, here x component is directed this way, and this flipping is described by these minus signs, which apply to x and y components of the electric field. Quite messy, I know. Now we need to do the same for transmitted fields. The procedure is pretty much analogous to what we have just done for the reflected fields. First of all, because we are dealing with the field that propagates in the negative direction of the z-axis, we are using the M- diode, which has K- in the Cartesian representation. That's because the field propagates downwards. But also remember that these diodes involve Kz negative. These are the z components of the wave vectors that take into account the substrate permittivity. Then for S polarization, the situation is very simple. We simply multiply the MS diodes by the Fresnel's TS for S polarization, which is very simple, very easy to calculate, and we obtain the S polarized part to the M diode. For P polarized part, again, we need to do this exercise with converting an electric field to the magnetic field and back into the electric fields, and we relate the magnetic fields by this Fresnel's TP, and we obtain in the end the following diode, where E, or I should write L, signifies that this diode relates the electric field component of incident and transmitted wave. And we don't have the minus here because in a transmitted wave, the transmitted wave sort of doesn't experience this flipping, which you see only in the reflected field, because the reflected field starts to propagate in the opposite direction, but transmitted field, it still propagates in the same direction. So electric fields do not flip in such a way. And by combining all of that together, we obtain sort of the final answer, at least some kind of closed form expression that expresses the Green's tensor in the substrate above the interface and in the substrate below the interface, where the diodes are given by the respective expressions. And I should add that we are using M minus here. Yeah, that's quite scary. It's very tedious. There's a lot of math involved. Even having this at hand, it is very, I agree, it is very difficult to obtain the final answer, but such is the problem. Again, because we are trying to combine two quite different geometries, we end up with a very scary, mathematically very scary answer. So anyway, no matter how scary it is, for any dielectric substrate with positive permittivity, it is possible to straightforwardly perform this integration, for example, numerically, and obtain an unambiguous answer. There are no poles in the integrand, and the integration is done easily. However, no, not yet. So now I want to discuss with you the possible different possibilities that can realize with dielectric substrates, and what the radiation patterns actually look like when we're dealing with the dipole emission close to a dielectric substrate. So these two pictures, taken from Principles of Non-Optics by Novotny, visualize the radiation pattern of a point electric dipole oriented at 60 degrees to the interface, placed at a different distance above a dielectric substrate. And they display strikingly different radiation patterns. And one can describe this behavior by separately addressing what happens in the superstrate and in the substrate. So in the upper half space, the radiation produced by the dipole is a result of interference between the two contributions, interference between the primary fields of the dipole and the reflected fields. And depending on the distance between the interface and the dipole, this interference can take pretty different forms, and the resulting radiation patterns will be very, very different. Generally, as you increase h, as you increase the distance, the radiation pattern will have more and more peaks. And as you decrease the radiation pattern, the interference diminishes, and you end up with a very relatively simple shape. In the substrate, however, radiation takes slightly different form. Generally, it can be divided into two contributions, so-called allowed light and forbidden light. Because the substrate is dielectric, there is the critical angle, the angle of total internal reflection. And if the dipole is located sufficiently far away from the substrate, at a distance of a few wavelengths, then the evanescent contributions of the primary fields, they decay sufficiently fast. And so everything that reaches the interface are just propagating waves. And when propagating waves are incident on a dielectric, they always get converted to radiation that propagates below the critical angle. So this is theta critical, which is described by the total internal reflection formula. So with the dipole, when any far field radiation is sent onto the dielectric substrate, it always propagates below the critical angle in the substrate. However, if the dipole is located at a sub-wavelength distance from the substrate, then the evanescent components of the primary fields, they do not decay sufficiently fast, and they do reach the interface. And when they do reach the interface, these evanescent components are transformed into propagating radiation into homogeneous waves, because they become allowed light. So a certain fraction of light goes at angles, propagate at angles beyond the critical angle, but this only happens when the dipole is located at distances, at sub-wavelength distances from the interface, so that the evanescent components of the primary fields, they do not decay very strongly before reaching the interface. But the situation becomes typically a bit more complicated when we have a metallic substrate. This is because the reflection and transmission coefficients for P-polarization, they may have poles on the real axis. These poles are related to the surface waves that we studied previously. These surface waves are located below the light line, and they typically appear as poles of the corresponding reflection coefficient. And when we perform the integration, we're going to see that our integration contour, so this is K parallel, that there is a pole exactly on the real axis. If the substrate is lossless, then this pole of reflection coefficient will appear exactly on the real axis. And we have to do something with this pole. We cannot integrate just straight across the pole. We cannot do that. So what we need to do is that we need to deform the integration path in a certain way. And this is a very, very, very technical subject. We don't have an opportunity to go into details. I'll just try to briefly explain you how this integration is done when we have a metallic substrate with potential poles of reflection coefficients. So what we can do in this case is that we can add a small dissipation to the substrate. And when we add a small dissipation to the substrate, the surface waves acquire finite propagation constant. They decay, meaning that propagation constant, beta, becomes complex valued. This means that this pole moves into upper half plane, in the upper complex half plane, and it goes here. And then we can easily perform the integration without any difficulties. And then we can take our dissipation that's added in the substrate, and we can take a limit of the dissipation to 0, and that will give us a physical answer. But this suggests another way of doing this problem, because we see that when we add a small dissipation, very small dissipation, the pole moves into upper half plane, upper complex half plane. That means that we can, in principle, avoid adding dissipation, but what we could do instead is that we can have a pole on the real axis, and we can deform the integration contour by going along a small semicircle just around below the pole. This will be our deformed integration contour. And by going in this way, we should be able to perform the integration and obtain the physically correct answer. Now, what some other works suggest is that we can complete this path by including integration over the negative axis, by closing it with a large semi-arc, and then by accounting for all these poles and branch cuts in the lower half space. But this is very technical. I'm not going to discuss this with you today, so I suggest that we stop here. And this brings me to the conclusion of today's lecture. So today we looked at a very complicated radiation problem, which is the problem of dipole radiation above the interface. We learned the tool of angular spectrum decomposition, which is done with the use of Weyl identity. we applied that tool of angular spectrum decomposition to the Sommerfeld problem. We obtained closed form expressions that describe the field distribution in the Sommerfeld problem. And we briefly discussed the resulting electric field and radiation patterns produced by dipole placed above an interface. Thank you, and see you next time, next week, when we discuss the final lecture in the first half of the course, devoted to the local density of states. And so basically we have 2 more lectures this term. We have lecture number 12, which finalizes the radiation section of our course. But then, because the schedule of the course is a bit uneven, we have also a 13th lecture, which I placed in the first term. And for that reason, the 13th lecture is going to be a bit different subject. It's going to be about the scattering problem. So I think after the next lecture, I'm going to discuss with you the intermediate exam. We're going to discuss that with you next week. And then I'll give you the 13th lecture, which will be a nice intro, a nice head start into scattering, which will be a subject of the next term, of the spring term. And depending on your schedule, we may have also a short lecture with your questions, for example, and maybe where I present some additions and corrections to mistake that I've done previously, for example, on lecture 2 about the pointing theorem. So that's the plan. Take care, and see you next week.